for our final project, we decided to 3D print a fidget spinner and use thermoforming for the packaging. The reasons why we chose this project is, first, 3D printing is a modern production method that is continuously growing throughout the world. And because of this, as a group, we decided that we wanted to gain practical experience in 3D printing. For most of us, this is our first time, so this will be a great experience. In addition, we feel CAD experience is extremely important in the engineering industry. So the most experience we can have in CAD software, the better. Lastly, we felt we needed a small little addition to this project. So we thought that everything in marketing needs packaging. And because of this, we felt we would try our hand at a basic thermoforming manufacturing process for this packaging.
Lessons we learned using CAD to design our project. We used Fusion 360 to design all our parts to make our fidget spinner and to make our mold for the thermal packaging process. When designing for 3D printing, we kept in mind what we learned in class on how plastic parts will shrink in size when cooling down during the printing process. With this knowledge, we had to design our parts to be slightly oversized or undersized to account for the thermal shrinking. For example, we were using bearings with a diameter of 1.18 inches. In our design, we wanted a snug fit but still had to oversize the hole by 1.5% to account for thermal shrinking. Our final design size for the bearing holes ended up being 1.19 inches, resulting in a very tight fit, making it so we did not have to use any adhesives to hold the bearing in place. This is quick animation of the CAD steps to make our fidget spinner body. Lessons we learned for the 3D printing process. So we used Cura cutting software to take our STL model file and convert it to G-code so the printer could print our fidget spinner. We learned a few good tips during our 3D printing process. First thing we learned was using wall thickness to our advantage to achieve our tight tolerances for the bearing holes. We used a 4-line wall thickness and a 40% infill to keep our body of the fidget spinner strong, lightweight, and also helped keep the total print time down. We also found changing the cooling for the printing to start on the 5th layer resulted in better tolerances and better build plate adhesion. Through our trials, we found the print speed of 55 millimeters per second resulted in the best print time for surface quality. Here we're in the Cura cutting software and we're using 40% infill with gyro pattern. Our cooling was set at 100% fan after the 5th layer, and we didn't need a build plate adhesion method. So we go down and slice our model file, and this is just breaking down our solid model into its individual layers. What's nice about the software is we can go up here and preview our individual layers. And this is the preview, and we can see the tool path for the 3D printer head on each individual layer as it'll print. And with this print, we have a estimated 3 hours and 33 minute print time.
Some lessons we learned in thermoforming is we need to heat the plastic uniformly and even. If not, it could be detrimental to the final product. We found that high temperatures would make the plastic turn a white color, and that's not the desired look that we're looking for. The thickness of the plastic is an important aspect. We found that you need a good balance between thick and thin plastic based on formability and desired shape. We found that the vacuum method that we used worked well, but it had some flaws. For example, there was warping in certain spots where we didn't want it to warp. As you can see, for the thermoforming, we created a box and made a bunch of holes at the top and created a big hole at the bottom that a vacuum hose can fit in. We heated the plastic up to a point of consistency to where it would form to the fidget spinner on the top, and then we turned on the vacuum and placed the plastic on top to create our desired shape.